restart the session. So our second speaker of this session is Travis Scrimshaw. So he's going to talk about refined real Grothendieck polynomials and last passage percolation. So please.
Thank you, and thank you for giving me the opportunity to speak here. So what I'm going to be talking about today is geometry, which I know makes absolutely no sense at a probability conference, and subsequently I'm going to move away very quickly from it, in part because I don't really understand the geometry much either. And what we're going to be talking about actually for the real meat of the talk will be kind of more combinatorial objects that I'm at least a little more comfortable with. So this is all based on work with Kohei-Mategi. And just to kind of start the talk, we'll go through some of the geometry that was the motivation for the main polynomials that we're going to be talking about, which are these refined dual Grothendieck polynomials. And then we'll be relating it to a random matrix model with last passage percolation, and talk about some of the results that follow from that. So getting into it, well, we're just going to take something called a complete flag. So you can think of vector space C to the n, and you start with the identity, or sorry, the zero space. You add a one-dimensional line, and then a two-dimensional plane, hence a flag variety. Maybe that'll display a little better. So yeah, so these are flags, and if we range over all possible such flags, this is the full or complete flag variety. And well, it's a nice linear algebra exercise to give to students that, well, we can find a matrix that transform this into the standard flag, where VI is just the first I coordinates, the span of all of those. And then this is stabilized by the upper triangular matrices. And so we can identify the complete flag variety with the Lie group GLN, this case over C, divided by its group of upper triangular matrices, which is called a Borel subgroup. And we can look at this and break this up into Borel orbits, and each of these orbits will be indexed by a permutation, and these are called Schubert cells. And then we take the closure of these under something called the Zariski topology, which, if you like topological spaces, this is a really horrible topology. It's not Hausdorff, but it's motivated by the study of ideals. And it turns out to be a very natural kind of topology to look at. We can take the closure of these Schubert cells, and these give us Schubert varieties, which have been very well studied from many different viewpoints. Why we care about them is because the Schubert varieties give us a very natural way to construct a basis for the cohomology ring of the flag variety. And then if we wanted to go a little bit further, and kind of from the geometry point of view, a common thing to do is look at things that are invariant under the maximal torus. And you can use this to build up a lot of the geometry, in particular, constructing a basis for the cohomology ring. Because the torus fixed points are in bijection with the permutations, and that basically allows us to work with the Schubert varieties. But for this talk, I'm not going to care so much about the full flag variety, but what you could call a two-step flag variety, where I start with the trivial subspace, and then I have a k-dimensional plane in between it, and then I have the full c to the n, that full vector space. And I want to look at the set of all of these. And this is the Grassmannian. And in the same way, we can produce orbits under the upper triangular matrices, and they're indexed by the torus fixed points. We can do all of that geometry that I was talking about earlier. And we can do the same sort of decomposition, but now the permutations are only allowed to have one descent. That's what this Grassmannian permutation means. It's a permutation that has exactly one descent in it. And that one descent will actually has to be at position k as well for this. And these are correspond naturally to partitions by kind of a Maya diagram or 0-1 sequence, depending upon the language you speak for this. But there's a natural bijection between Grassmannian permutations and partitions inside of an n minus k by k rectangle. And we can take the closure of these orbits, and these are, again, Schubert varieties living inside of the Grassmannian. And yeah, that's what I said. Grassmannian permutations are permutations with a single descent. And we can use the Schubert varieties, again, to build a basis for the cohomology ring of the Grassmannian. But we kind of understand this fairly well because these representatives are Schur functions that sit inside of this k by n minus k rectangle. And the multiplication in the cohomology ring is just the product of Schur functions. And then you just get rid of terms that fall outside of the rectangle. So that's fine. You know, it's good that we know the structure, but we want something that's a little bit richer than it because we lose a lot of information going to cohomology. So to get a little bit more information, we look at the K-theory ring of the Grassmannian, or the flag variety. And something that's very useful is actually looking at the singularities of the Schubert variety. So you can have kind of pinches like this, or double points like this. These are types of singularities that can appear in the variety world that, you know, it's basically measuring the point. They're points where you fail to be a manifold, more or less. And there's a well-known resolution of these singularities called a Bott-Samuelson resolution. And we can take the push forward of this resolution, and we can obtain a basis for the K-theory. And effectively, what we have then is a basis for the K-theory given by Schubert varieties again. And as just a technical point, in case anyone knows about Bott-Samuelson resolutions, they depend upon a choice of reduced expression, but the K-theory class is actually independent of this choice. So it's well-defined, indexing it by the permutation. And all of this geometry is great, but we want to actually do some computations with it. And, you know, in the cohomology case, these are given by Schur functions, but we want to look at the K-theory analog of this. And that's where Grothendieck polynomials enter our picture. So as in the cohomology case, we have classical combinatorial objects of semi-standard Young tableau, which is if we have a partition, let's say like this, then we can fill it with positive integers such that the rows are weakly increasing and columns are strictly increasing. And what we want at the K-theory is, instead of integers, we want to replace it by finite but non-empty subsets of positive integers. So if I was a little better, let me, my example here, I'll fill that with a 4. I can take something like 2 and 3 here and add it in, and add a 2 there, and add like a 7 there. And this would be a set value tableau, but I still need a notion of semi-standard because I don't want to just fill it with anything. So the condition, the semi-standard condition, what it becomes is I take the maximum entry here in any kind of local place, and I compare it to the entries to its right, and the weakly increasing condition means that the maximum of A is less than or equal to the minimum of B, and the column increasing condition becomes the maximum of A is strictly less than the minimum of C. And we can see in this little example that I've drawn up here in the corner that this holds for all of these cases. And then the weight is just counting the number of 1s, counting the number of 2s in different variables. So x1 for the number of 1s, x2 to the number of 2s, in the same sort of way you would do for Schur functions with semi-standard Young tableau. And then we're going to add an extra condition on this, which is called the excess, and that's just going to measure how far it is from being a semi-standard tableau. So in this example here, I'd have x1, x2 squared, x3 cubed, x to the 4, x to the 5, x to the 7, and the excess is 1, 2, 3, 4, corresponding to the number of entries here in red, for instance. And so a symmetric Grothendieck function will just be the sum over all set value tableau of shape lambda, and we just take the weight and then we multiply it by this extra parameter beta to the excess. And this is a symmetric function in the same way for Schur functions, but you have to work a little bit harder to see it, at least from like a Bender-Knuth type, kind of combinatorial arguments, but it's not too difficult depending upon how you want to look at it. And if we want an honest polynomial, we can just restrict to n variables. And these symmetric Grothendieck polynomials are precisely the representatives for the K-theory ring. And we just have to multiply them together. It's not too hard, but it is a non-trivial fact that multiplication of Grothendieck polynomials, that this really is a basis, and it's we're working in a completion of the ring of symmetric functions because we have this beta parameter, and we can have beta get arbitrarily large, but it turns out that when we multiply them and expand it in terms of Grothendieck's, we get a finite sum back again, and then we can then, to get the representatives of the K-theory ring, we just lop off anything that falls outside of a k by n minus k rectangle. So now, armed with our Grothendieck polynomials, our Grothendieck functions, we can look at their Schur expansion, which is again kind of filtered, but it still is, because of that filtration, it's still sufficiently nice So we can do stuff that we normally want to do, at least for me in the land of symmetric functions, which is find a dual basis with respect to the Hall inner product, which is kind of the canonical inner product on the ring of symmetric functions. And the Schur functions, you can define it by saying the Schur functions are an orthonormal basis. And so we have our Grothendieck polynomials, but turns out the objects that I want to focus on for this talk is the dual basis to this, which are called the dual Grothendieck polynomials or functions, depending upon if we have finitely many variables or not. And these have a combinatorial interpretation given by Lamb and Pilavsky, which says it's the sum over reverse plane partitions, where a reverse plane partition is kind of like a semi-standard Young tableau, except we weaken the column condition to be weakly increasing as well. But we don't want to do the weight like we would for a semi-standard Young tableau. We actually only want the, one way you can think of it is you want to count the columns that contain an I. Or you can also think of it as the boxes that are filled with I, such that the I immediately below it, or there's no I immediately below it. So if you have something like this, then, and then let's say a K where K is greater than I, this I contributes to the weight, and this does not. So this beta parameter is, again, just measuring how far we are from being a semi-standard Young tableau, because it's just counting those boxes that have an I immediately below it. But we can actually get a little bit more information out of this. We can, instead of just a generic beta parameter, we can give a parameter based upon the row that this repetition occurred. And we'll call that Tj if it occurs in row J. And so we can refine the dual Grothendieck polynomials by these additional parameters. And it turns out that this remains a symmetric function. And this was this notion of refinement and proving that it was a symmetric function was done by Galashin, Grinberg, and Liu. And this turns out to be a polynomial when we have finitely many variables in the same way as before. But because the Grothendieck polynomials are upper filtered, the duals are lower filtered, and so the expansion into Schur functions is always a finite sum. And so it's just an example, so that we actually have one here. If we have two variables, x1 and x2, and we look at the shape 2, 1, these are all of the reverse plane partitions. And this block here is multiplied by T1 because we have the repetition in the first row, like this. Any questions so far? I saw there was something in the chat as well.
So sorry, I didn't mean it to put it just now. Sorry. It's related to the previous question, sorry.
I see. All right. And so we have this sum over semi-standard tableau. It's a symmetric reverse plane partitions. It's a symmetric function, but it turns out that it is also Schur positive. and the coefficients also have a nice combinatorial interpretation. And how Lamb and Pielowski proved this is they did a variation of RSK called, which I've been calling the inflation map, because you're taking a smaller semi-standard tableau shape mu that fits inside lambda, and you're just inflating it until you get to a shape lambda, and you're recording kind of the positions where you do this. And because I cannot resist, I have to at least mention that there's a crystal structure on reverse plane partitions given by Pavel Galoshin. And this is another way you can show that it's Schur positive. And in fact, how Lamb and Pielowski grouped the reverse plane partitions together into Schur functions is precisely given by this crystal structure. And when you look at the crystal structure, it actually becomes very easy to show that this this decomposition holds in the refined setting. So I'm attributing this to Lamb and Pielowski, where if you look at their bijection, it's not a very difficult exercise to trace through that it works in the refined setting. They were working when all of the t's were equal to a common parameter beta, or maybe they were working in when beta is -1, which is kind of the true K theory versus the connective K theory, but minor point. So, and then you can also see this from Pavel's work as well. So what are these coefficients? Well, they are basically semi-standard Young tableau of a skew shape now of lambda minus mu. But you have this additional flagging condition where row I has to be, the entries that appear in row I all have to be strictly less than I. So as a consequence of this, we have to have that lambda mu1 is equal to lambda 1 in order for there to be an elegant tableau, because we can't have any entries in the first row because we have to fill it with positive integers. So now that I've thoroughly bored the audience, maybe I can perk everyone back up, because now I'm starting to talk about some probability theory. And what I'm going to be doing is I'm going to be taking a random matrix, and I'm going to have each of the entries be given by a geometric distribution. And the ij entry will depend upon two parameters, ti and xj, in kind of the, just take their products, and that's going to give you the geometric distribution. And where these are coming from, you can think of it as being a refinement of the passage time coming from the totally asymmetric simple exclusion process, which I'm sure everyone here knows as TASEP, and starting with the step initial condition and having the particles hop with rate p, or sorry, with probability p. And how we build that kind of connection is in our matrix. We start with in the bottom left-hand corner, and we're going to move up. We're going to have L north steps and N east steps. And this is going to give us a path in this matrix. And we're going to define the weight of the path to be the sum of the entries. And the last passage time will be the maximum over all such paths, say from the bottom left-hand corner to this spot that's shifted up by L and right by E, sorry, right by N. And this will be the last passage time. And then I'm just going to build this vector like so. And so as an example, let's say for this entry here. I've written the last passage time as the subscript. And I have a few different paths. I can go kind of up like this. And as another one, I can go over, up, and over like this, or even just going like over and up like that. And if I sum over all of those, well, I get 2, like say this green path, I get 2 plus 1, which gives me 3. If I did the red path, I get 2, because I have 1 plus 1 and then a bunch of zeros and stuff like that. So and how we can build the connection between this combinatorial geometric picture and the last passage time of these random, or well, really these random matrices at just initially, is that we just have the wij entry, or sorry, the ij entry of W, this random matrix, just count the number of j's in row I of a reverse plane partition where that box J, filled with a J in row I does not have a J below it. In other words, it's counting the J's that contribute to the weight of the reverse plane partition. And this gives us a bijection. So as an example, what we have is right here, where the this one gives us this entry here. This one is this entry. This 4. Oops. That's the wrong 4. This 4 gives us this entry. And these 2 3s give us this entry. And that's the bijection. And it's not too hard to construct the inverse because you're just basically summing the last passage times, which is the next thing here. In particular, as we saw in the previous slide, the last passage times of this matrix for these entries on the right is 3, 3, 2, which corresponds to our partition here. And then if I get rid of this 1, I get 2, 2, 2, which is what I get when I remove the 3s. And I get 2, 1, 0, 2, 1, 0, which is what I get once I remove the 3s here. And so this bijection is great. And Yeliussizov actually showed that this bijection it works if you're conditioning on the probability of the matrix when you have the t equals x equals the square root of q. But this also works almost at the level of the refined statistics. But you have to do this extra kind of, you actually want t inverse, and then you have to multiply everything by t to the lambda. So as an example, just to illustrate what's going on, well, if I compute the refined, I have these entries here, this 1, this 4, and this 3 contribute to the T1 squared T2, but over in the random matrix side, well, the exponents of T are just the row sums, and the exponents of X are just the column sums. And so to translate between the two, well, I have to scale everything by, come on, let me annotate, please. There we go. T1 cubed, T2 cubed, T3 squared. And then if I just multiply by T1 to the -2, T2 to the -1, and I see a typo there. There should not be a T cubed. I get precisely this. All right. So we have this this matrix filled with non-negative integers. And a natural thing to do to this, at least if you're a good combinatorialist and you read Stanley's EC2 chapter 7 many times, is, well, let's do RSK on this. And so we get a pair of semi-standard tableau P and Q. And this insertion tableau P will correspond to that Schur decomposition that I talked about earlier. And the recording tableau Q should correspond to an elegant tableau. It does, but you have to work just a little bit to actually get that relationship. Because what you get is a recording tableau of the same shape, but you're going to have conditions on it coming from the shape lambda of the reverse plane partition. In particular, the first row, if you look at the entries less than or equal to I, it has to equal to lambda I. And if we translate this into a Gelfand-Setlin pattern, if you know what those are, it means that the left-hand side has to be precisely lambda. And this was the description given by Decker and Warren, but they were looking at the case when the x variables were equal to 1. So let's go back to, let's do a slightly different example here, but still everything of the shape 3, 3, 2. And I have a reverse plane partition, and then I have under the bijection phi, this 0, 1 matrix. And now I'm going to do something slightly different. And I'm going to actually, for this purpose, read my matrix kind of in a non-standard way from bottom to top. And so this 2 will correspond to these bi letters here. And then you can work out the rest. It ends up being this bi word, which when you do RSK, maps over to here. And if I look at the Gelfand-Setlin pattern for this, well, if you've not seen it before, the top row is the shape with all of the entries less than or equal to 3. The second row is with all of the entries less than or equal to 2. And the kind of first row is less than or equal to 1. And as promised, the left-hand side of this is precisely our shape lambda, given by 332. And so this is great. We have our straight shapes, but we can do something a little bit better because we want to look at skew shapes because these are a little more general, and it allows you kind of to build up, at least on the combinatorial side, it allows you to build up pieces one by, entry by entry. But if you're coming from the probability side, well, you have this kind of starting from nothing and building up, but you should be able to start from somewhere else and continue, and this transition probability. And so you can actually show that this transition probability is a dual Grothendieck polynomial up to that same sort of dealing with the inverse and changing things over. And then you have this normalization factor that just comes from all of the entries for the geometric distribution have this kind of leading term out there that we just have to normalize out by. And how you can show that is by restricting to the single variable case. And you can just look at what happens when you have one variable, which is the same as saying one entry, let's call that n, and seeing if you have a shape lambda, a shape mu sitting inside of it, look at the skew shape, fill all of the entries with n. What do you get? You can show that it's precisely given by this formula. And then from there, you just use the fact that, well, a reverse plane partition is just given by starting with the ones and then the twos and then the threes in all possible kind of chains of partitions given by inclusion. And then because we're working in a probability setting, we know that the sum of all possible states has to be 1. That very fundamental probabilistic statement that we love to teach our students probably in the first day. You can't have anything that doesn't actually exist, and you can't have more than what exists. So if we just sum over all possible states, we actually get a Cauchy-Littlewood type identity by just dividing out by these factors, which was originally proven by Yeliussizov in a paper that has recently been published. And how he did it was using some algebraic manipulations, but we essentially get this identity for free from the probability viewpoint. And something else that we were able to prove is that you can construct a dual Jacobi-Trudi type formula for the refined dual Grothendieck polynomials. And this was also independently proven by Jung-Soo Kim at the same time. But our proof is somewhat probabilistic. It's more based on algebraic and determinantal manipulations. We followed what Johansson did in his 2010 paper, I think it was, with on Mixner ensembles. I forget the exact title. I think I have, let me actually, since I have, I should give a proper reference here. Yeah, a multi-dimensional Markov chain and the Mixner ensemble is 2010 paper like that. We just refined what he did there, which is when x equals t equals the square root of, and his parameter was q. This was also effectively simultaneously proved by Iwo, but having the T parameters all being equal to beta by using the boson-fermion correspondence Wick's formula and a very mathematical physics approach. And then Amanov and Yeliussizov also showed this by using a sign reversing involution and some very intricate kind of combinatorial arguments. So we have 4 different proofs, at least in special cases of this. And we have kind of a normal Jacobi-Trudi formula. And this was independently proven by Jong-Soo Kim as well using plathistic techniques. But we also found out that Johansson and Raman proved this in the same way that Motegi and I did at basically the same time. And again, Iwo proved it using boson-fermion and Wick's formula for T equals beta. And when T equals beta, there's involution that you can use on symmetric functions where you get this as a consequence of Amanov and Yeliussizov's work. But you can't, this proof doesn't work in the general case. You don't have this involution on symmetric functions in the refined setting. And this also appears in Decker and Warren's work when all of the x parameters are equal to 1. It's the transition kernel for another kind of particle process where particles can hop with geometric rates and push other particles along. It's case A in their paper. And then from our techniques and following Johansson's work, we were able to just refine it. And again, simultaneously with Johansson and Raman, we're able to get these determinantal of integral formulas for the refined dual Grothendieck polynomials. And if we look at the straight shape case, we can evaluate this determinant, pull some stuff out, and end up with this integral formula for the refined dual Grothendieck's. And when we specialize all of the T parameters to being 0, we recover the what I've been told is a famous integral formula for the Schur functions as a consequence. So where do we go from here? Well, since this is a workshop on positive temperatures, I at least have to mention something about positive temperatures. Unfortunately, all I can mention is, please help me. I don't know anything about how to talk about the positive temperature version of this, which from what I've been told means instead of the last passage percolation, we are instead of taking the maximum, we're summing over everything and taking the products of the weights. And in other words, we're taking a rational lifting of kind of a tropical object, at least that's what it would be kind of in my terminology. And there's a notion of a rational lifting of a crystal, which is called a geometric crystal. So what is the analog of reverse plane partitions? What's the analog of the geometric crystal of, that lifting of that crystal structure? Yeliussizov's bijection, all of these kinds of things. Like I can give some ideas about what they are, but what other kind of structures exist and what's the correct way to do all of this lifting and connecting it with positive temperature stuff. Then on the other side, we had the Grothendieck polynomials. I would be curious to know what kind of particle process we could get by using the set valued tableau, and could we get something interesting from that from a probabilistic point of view, and then be able to derive some additional identities from that. And then we had geometric weights in our random matrix, but what happens on the combinatorial side when we change those to some other kind of distribution. Like in particular, if you change it to the exponential, and then you have continuous taste-up, what does this mean in terms of the combinatorics for the Grothendieck polynomials and their duals and stuff like that? Can we say something about the more combinatorial side? And then we can relate the refined dual Grothendieck polynomials with the Schur process, because we're in the Schur process, if we think of it as being integrable systems type thing, we're basically splitting it. The Schur process splits it along here, and that gives us our shape lambda, where if you've not seen this before, you're kind of taking paths that go over and come back like this, where they all are ending kind of bunched together like this. So this is what's happening on the Schur measure side. But on the refined side, what we're doing is we're actually taking a cut kind of in a slightly different way. Actually, I guess I have my picture slightly wrong here. For the Schur process, oops, no, I want to draw here. I want them to continue on all the way up here. And let me write this as, and so this kind of cut along here gives us a partition eta, if I instead call this eta over here. So it's cutting the same picture in two different ways. But what happens if we replace the Schur measure with something else, like a McDonald measure? Can we use this kind of combinatorial data, pull it back, and get something interesting, some kind of QT deformation of the Grothendieck and their duals, something like that? So these are all questions that I would like to find answers for, and would definitely appreciate some help from the audience about this. So thank you very much.